Good day, my name is Wing Pak. I'm one of the instructors in the Civil 1232 course. Today we're going to talk about phase 1 of the bridge contest. In the next 50 minutes, we'll go over the purpose of phase 1 in terms of the overall bridge contest, the analysis program which you will be using in phase 1, the requirements and specifications which you'll need to meet for your phase 1 design, how you'll be graded for phase 1, how you can create a bridge design in the Bridge Designer program, and finally ways in which you can improve your bridge design in Bridge Designer. The purpose of the phase 1 of the bridge contest in Civil 1232 is to introduce students to the engineering design process, whereby you're presented with some problem, and as good engineers, technicians, and technologists, you need to use your skills in math and science and the technologies which you have available at hand to come up with a solution which is ideal or to as close to ideal as possible. For phase 1, the problem that we have is that we have a river valley which we want to build a bridge to span across. You as a technologist will try to come up with the best design for this bridge. In phase 1, we're going to assume that in terms of comparing the various designs which are possible, we'll use a cost as our criteria. The least cost design is going to be our best design. Also in phase 1, you'll learn about truss bridges and how they work. For example, how certain members of your truss bridge will be in compression and others will be in tension. How for truss bridges, in terms of the height of the bridge versus the span, there is an ideal range of heights where the design will be as close to as being ideal. How in terms of your panels for your bridge, each panel needs to be triangulated for the bridge to be stable. The information that you will learn in phase 1 about how truss bridges work, you can apply and use in phase 2 of the bridge contest. In phase 2, you will design the actual bridge, which you will construct from balsa wood at the end of the term. Also in phase 2, you'll be working with a different set of specifications. So don't worry if the design from your phase 1 and phase 2 are not the same, because most likely they will not be. In terms of the specific requirements for phase 1, you'll need to refer to the Blackboard folder for Civil 1232. So go to Blackboard, look under course for Civil 1232 statics. So on the left hand side, you're going to find bridge contest. So click on bridge contests and scroll down under preliminary design, bridge designer, or where you're going to find your specifications for phase 1. We modify and vary these from year to year, so make sure you use the specification for your year and term. For this video and our demonstration, we're going to be using the parameters from the winter 2016 term. For this video, we're going to use the following parameters. We're going to set the bridge deck elevation to be 16 meters. We're going to set the support configurations to standard abutments, no pier, one span, no cable anchorages. For the bridge deck, we're going to use high strength concrete, 0.15 meters thick. The loading for our bridge will be a standard 225 kilonewton truck 2-lane load. In terms of our bridge, it will be a single span overhead bridge. None of the members of the bridge can extend below the support level or bridge. So what do I mean by that? So here we have two examples. The top one is an overhead bridge configuration, whereby in terms of all the members of the bridge, all the members are above the two supports on either side of the bridge. This is acceptable. The bottom one is a below deck bridge configuration, whereby members, or in this case all the members essentially, are below the support level of the two piers at either end of the bridge. For this last example, this is not acceptable. How will you be graded for phase 1? Bridge Designer calculates a cost for each bridge design. we're going to rank all the groups in terms of the cost from highest to lowest. The group with the lowest cost will be given 100% for phase 1, and the group with the highest cost will be given 50%. Groups in between will be given a prorated mark from 100% to 50%. Later on in this video, when we start looking at the actual designs from Bridge Designer, we're going to go into detail in terms of how Bridge Designer actually calculates a cost for your bridge design. In phase 1, we'll use an analysis program called Bridge Designer. So we're going to go to the website https bridgecontest.org. This software is used as part of the Engineering Encounter Bridge Contest, which is held each year in the US for middle schools and high school students. This contest was originally created, sponsored, and ran by the West Point Military Academy in the US and was first held in 2002. Since then, the running of this contest has been taken over by a non-profit organization called Engineering Encounters, and the main sponsors of this contest are now the American Society of Civil Engineers and Dell Computers. In the contest, students are presented with a river valley which they need to design a virtual bridge to span across. There are many variables which can be varied in terms of the bridge design. These include the height of the bridge above the river valley, the number and type of bridge supports used, the grade of concrete used for the bridge deck, the bridge geometry, the grade of structural steel used. In terms of program, 3 different grades of structural steel are available for you to use. From weakest to strongest, these are carbon steel, high strength low alloy steel, and quenched and tempered steel. Also, 2 different cross sections of steel members are available for you to use for each steel grade. These are square tubes and square bars. You can use different sizes of these tubes and bars for the members of your bridge. For phase 1 of our contest, we're going to fix most of these parameters. The only thing that will vary from group to group is the cost of the actual steel bridge of your design. How will you create a bridge design in Bridge Designer? First, you're going to need to download and use the current version of Bridge Designer from the Engineering Encounter Bridge Contest website. Download the current version of the program. So make sure again to use the current version, otherwise you're going to be disqualified from phase 1. If you are taking this course in winter 2016, you want to make sure you use the 2016 version of the program. Similarly, if you're taking the course in winter 2017, you're going to need to use the 2017 version of the program. In this demonstration, we're going to be using the 2016 version of the Bridge Designer program. So go ahead and download the Bridge Designer program. You're going to need to use the Windows version of the program. Save the download package onto your computer. So I'm going to be using Mozilla Firefox. So the program is going to be downloaded to the download folder on my computer. There it is right there. It's called Setup BDV. Because I'm using the 2016 version, it's 16j.exe. We're going to run this download package from this folder. Click on Run to allow the program to run on your computer. Follow the prompts. You can press Next. I agree to the license agreement. Press Next to where the program installs this software to on your computer. You can select Install for everyone using this computer in terms of the option and press Next. Leave the destination folder to the default. Press Next. and just press install. If everything goes smoothly, the program should be installed on your computer. You can access and run this piece of software by going to the startup button on the bottom left corner of your laptop. All programs. It's going to be under a folder called Bridge Designer. In my case, it's 2016 version of the program. And there's two versions of this program, one for older computers and one for just normal computers. Well, we're just going to run the second version, Bridge Designer 2016, second edition. Recommend that you save a shortcut of this program to your desktop. So that's what we're going to do right now. We're going to right click on this link, select the send to desktop create shortcut option, and a shortcut should be created on your desktop for this software. Now we're just going to start up this program. We're going to double click on the icon on our desktop. On first start up the program, a series of tips a day will be displayed, which suggests that you go through these at least once. There's about 25 of these tips. Also on first startup, you're going to need to create a new bridge design. So press OK to that. Next, you're going to need to select some of the parameters used by the program. So on the number one, read the design requirements. We're going to press next to this. In terms of the second screen, it asks you whether you want to enter the local contest. We are not participating as in part of the overall bridge contest. In terms of this engineer encounter bridge contest, we'll say no to that. We're going to press next to the screen. We're going to start entering some of the parameters for our bridge, which correspond to phase 1 of our contest. Deck elevation, we're going to set to 16 meters. Support configuration, we're going to leave that as standard abutments. Next option below that, it allows us to select no piers, one span, or piers with a 2-span condition. So right now you leave it as the first option, no piers. It basically, we're specifying a single span bridge from support to support. If we choose the second option, piers 2-span, this will introduce a middle pier at the middle of your bridge. The option below allows you to specify the height of this pier if you decide to use it. So let's just leave our selection at no piers, 1 span. Last set of options available at the very bottom. There's no cable anchorages, 1 cable anchorage, 2 cable anchorage. We're going to leave it as no cable anchorages. Selecting either of the last 2 features allows you to provide a cables anchorage if you were designing a cable stayed bridge. So we're going to press next now, which brings up to screen number 4, which allows us to specify the deck material as well as the truck loading. So for the deck material, for our example, our video, we're going to select high strength concrete. Truck loading, we're going to leave this as standard 225 kilonewton truck, 2-lane loading. For your particular year, your particular term, make sure you use the parameters, the deck material, and the truck loading specified on Blackboard. So on this screen, next, we're going to press the next at the bottom of this window. Screen number 5 allows us to use a number of preset truss templates in terms of the configuration of your bridge. We recommend that you do not use these. This allows for the greatest flexibility in terms of your design. So for screen number 5, we're going to select none at the very top of the selections. Then we're going to select the next option brings us to screen number 6. On this screen, under design by, you're gonna put your name. So I'm gonna put my name, Wayne Pack. If you work with a partner, put your partner's name as well. Under project ID, you're gonna put the year in which you work on this contest. So for me, it's 2016, and we're gonna follow that by bridge contest. So we're done with that. We're gonna press next. Screen number 7, we're gonna press finish, and we're set to go. We're all set to create our bridge design in Bridge Designer now. As you can see initially, the program creates the bridge deck for you, as well as all the joints along the bottom of the bridge. I'm going to use this as the initial starting point to create our design in Bridge Designer and add to it. The bridge design which I'll be creating will be this one here. It's a simple bridge with a bowstring geometry. The middle of the bridge will be 7 meters above the bridge deck. Then the height of the bridge will gradually decrease from the middle to 6 meters, then 5 meters from the bottom of the bridge. The top members of the bridge, these are referred to as the top chords. I'm going to make these 240 by 240 by 12 tube members. I'm going to use carbon steel for all the members of my bridge. The bottom members of the bridge are referred to as the bottom chord. For these members, I'm going to use 240 by 240 by 12 tube members as well. The verticals of my bridge, these are called verticals. I'm going to use 130 by 130 by 6 tubes for these members. The incline members between the top and the bottom chords, these are referred to as the diagonals. I'm going to make these 140 by 140 by 7 tubes. This is going to be my initial bridge design. Over the course of this video, I'm going to take this initial design and I'm going to show you some tips whereby you can incrementally change the design and gradually reduce the cost of your bridge. Alright, now we need to create the remaining joints in our bridge. We can do this by using the joint icon on our toolbox right here, or we can go to the very top along the menu. Under Tools and Joints, you can use this joint creation icon at the very top. To create a joint, just with your mouse, just left click anywhere on your screen. There are scales along the left and bottom to help you place your joints on your workspace. If at any time you make a mistake and you want to delete a joint, use the erase icon in the toolbox. This icon with the eraser tip at the very end. So we're just going to create all the joints on our bridge. One by one, we're going to do this. So now we're going to just fast forward. All our joints are created. Now we're ready to create the members in our bridge. Also as well, we want to assign the materials grade, whether the material we're using is a carbon steel, high strength, low alloy steel, or quench and temper steel, the type of profiles we're using in our steel members, as well as the size of these members. To assign these 3 properties, there are 3 pull down boxes at the very top of your screen. One is for the type of steel which you're using, which would be carbon steel, high strength, low alloy steel, quench and temper steel. Next to that is your profile, solid bars or hollow tubes. And next is corresponding sizes corresponding to the bars or tubes which you use. Initially, we want to create all the top chord members followed by all the bottom chord members. We want to make both of these carbon steel tubes 240 by 240 by 12. So we're just going to make the proper selection in our pull down boxes. To create the members, we left click with our mouse on a joint, then we drag and release to where we want that member to end. If you have a continuous member which spans across several joints, you're going to have to break the members into smaller pieces between the individual joints. The reason why is that the Bridge Designer program isn't smart enough to know whether you have a connection between your verticals and your diagonals and your chord members otherwise. So you need to basically segment your chord members into smaller pieces and not just draw one continuous piece across. Now we're going to create the verticals. All the verticals are going to be again carbon steel. They're going to be tubes. The members for these verticals are 130 by 130 by 6. Now we're going to create the diagonals. These are also going to be carbon steel tube members. These are going to be 140 by 140 by 7. Now we're ready to run our analysis. We can do this either one of two ways. We can go to the run the load test animation icon from your toolbar along the very top, or you can go to tests, and from that load test, and this will run your analysis. Initially, the programs check to see if the bridge is strong enough to support its own weight. If this is okay, then the program adds the truck loading. If the truck can get across from one side of the bridge to the other, your design is strong enough. As you can see, our design was not adequate and the truck was not able to cross from one side to the other. It's inside. Let's go back to our drawing board and our workspace. So go along the very top along your menu bar, your toolbar, select this icon right here. This allows you to go back to your workspace. In terms of your bridge designs, all your panels or your bridges of your bridge has to be triangulated. So what do we mean by that? So let's try deleting one of the diagonal members in our bridge. If we run our analysis, the program would actually tell you that your structural model is unstable. It gives you 4 examples of this. Now you go through each one of these examples. It explains to you why your bridge is unstable. So for example, this one here, which matches what we have, whereby this panel is not triangulated. Example number 2, you could do the same thing. Select it, press next. It shows you again why your panels, your bridge has to be triangulated. Otherwise, something funny in your bridge will happen. Same thing for example number 3. Select that. Let's just press next to see what happens. There you go. Another reason why your bridge has to be triangulated. Also, you can check example number 4. Press next and see what happens there as well. So let's go back to our bridge. Let's add back the diagonal member which we just deleted. That's in place. We know that this bridge doesn't work. In terms of the program highlights on the left side graphically and also highlights on the right side in terms of this table which members have failed. So the members which failed, these are shown as a hatched on the left side on this graphical display. In terms of the right hand side, in terms of the table, these are highlighted in red. So let's focus on the table on the right and talk about some of the information which is provided here. The first column is in the table is the member number. Each member in our truss design is assigned a number. Next column over is the material type. So what type of steel did you use in your design? Was it a carbon steel? Was it a high strength low alloy steel? Was it a quenched or tempered steel? Next column over is the cross section which you use, whether it's a tube or bar section. Next column over, it's the size for the member. Next column over is the member length. And the next column over is the slenderness. Column 6 is the slenderness ratio of the member. The larger this member, the more slender the member is compared to its length. In terms of the Bridge Designer program, the program uses this number to calculate the compression strength of a member. In terms of the program, there's a restriction placed on this ratio, and this ratio cannot exceed 300. So let's take one of these members. Let's try changing it such that the slenderness ratio is greater than 300 and see what happens. And we're going to change that to an HSS 30 by 30 by 2 member. So the program's going to give you a warning, and it's going to highlight the slenderness ratio for this member as a magenta. When you try to rerun the program, it's going to refuse to run, and it's going to tell you that you need to increase the size of the member such that the slenderness ratio is 300 or less. The next two columns are the ratio for the compression force versus strength and the tension force versus strength in our member. How do we use these in our design? Well, these are measures of how each member is overloaded or underutilized. For example, if the compression force versus strength ratio is greater than 1, this means that the compression force in the member is greater than its strength, and that the member is overloaded. In the end, you're going to need to increase the size of this member. On the other hand, if the ratio is less than 1, this means this member is underutilized, and that there's going to be some reserve in this member, and that you can look into reducing the size of this member and perhaps reducing the overall cost of your bridge. Ultimately, you want to use member sizes where the strength, resistance ratio, and tension and or compression are as close to 1 as possible, but do not exceed 1. As a side note, if either the strength resistance ratio for compression or tension is 0, that means that member is in pure tension or in pure compression. In terms of our design, 2 verticals in the bridge actually failed. They have a force strength ratio and tension of about 0.1, but in compression, the force strength ratio is about 1.1, meaning that the member sees a small tension force, but in compression, the member is actually overloaded. Now we're going to try to get an acceptable design. Let's try to increase the 2 verticals which fail to a larger size. So let's try to use a carbon steel. Let's use a tube. You try to use a 140 by 140 by 7 member. Let's rerun the analysis. So the bridge works for its own weight. The truck can get across now, and that the design actually works. The cost for this bridge is about $233,000. Now let's look at the cost report generated by this program. You can access the cost report by going to Reports and cost calculations. At the very top, we have the materials costs. For each grade of steel, depending whether you use a tube or a bar profile, there's a cost for each kg of material that you use. I summarize this in terms of this table. With each higher grade of steel, there's going to be an increased cost. The strength of each grade of steel is measured in terms of a material property called yield strength, which is expressed as a pressure in units of pounds per square inch. In terms of the cost of tube versus bars for the same grade of steel, tubes are more expensive than bars. This is because to fabricate tubes, steel manufacturers need to make steel plates. These are usually bent into shape of a steel tube. Then along the seam, a continuous bead of weld is provided to close off the tube. There's just a lot more work involved to fabricate a tube versus a solid steel bar. Thus, you have the higher cost between these two items. In terms of the material cost for our current design, we have two trusses, one on each side of the bridge. For each truss, we have 9,618 kgs of carbon steel tubes at $6.30 per kilograms of steel. We times this by two sides for a total materials cost of $121,000. Next, we have the connections cost. For each joint in your truss, there is an additional cost of about $400 per joint. The more joints you have in your bridge, the higher your bridge cost is. If you think about this, there's a rationale behind this. With each joint which you add, there's a technician or engineer which needs to sit down, design, and detail how all the members fit together and are connected to the joint. What thickness the connection plate has to be, how many and what size of bolts are needed at each member to connect into the joint. Then you have a draftsperson who needs to draft up this connection. From the drawing which is produced, this is passed to some guy in the shop who fabricates the joint. For each joint and connection, he needs to cut the material plate to size. He needs to drill out all the holes in that connection plate, as well as all the holes in the members connected to that joint. Finally, you have the worker on site who needs to put the bridge together. The more joints there are in your design, the more members that worker has to handle and erect on site. In terms of the connection cost for this design, there are 18 joints at $400 per joint, times 2 trusses, 1 per side of your bridge, for a total connection cost of about $14,400. Next, we have the product cost. Each combination of steel grade plus cross-section plus sizing is grouped as a product. So right now we have 3 products in our design. Initially, we have one, which is a 130 by 130 by 6 carbon tube. We have another, which is a 140 by 140 by 7 carbon tube. And for our top and bottom cords, we have a 240 by 240 by 12 carbon tube. Each product which you use in your design adds $1,000 to your cost. Again, there's a logic behind this. Imagine you're a steel fabricator, and let's say that you have a job whereby the engineer, the technician really went crazy and overboard. He decided to optimize all the members in the bridge so that each one is different and that each one is just on the verge of failing. He's going to use a different size of tube or bar for each one of the members in his bridge. As a fabricator, think of all the extra work you have to do. You have to order all this extra material. From each batch material, you're probably going to use only a few meters of material. The rest of the material is probably just going to sit in your shop waiting for another job in which you can use that material. Without any doubt, this is going to cut into your profit margin and your productivity. Generally, you want to come up with a design which uses as few products as possible. However, if you just use one product for your entire bridge and made all the members the same in terms of steel grade, profile, and sizing, your material cost will be sky high. In the end, you want to come up with a balance in your design whereby you have the best combination of material costs, connection costs, and product costs. So right now, with 3 products at $1,000 each, this gives us a total product cost of $3,000. Finally, we have the site cost. The site cost includes the cost of your bridge deck, excavation, and support. For example, which we're using in this video, the site cost is $94,500. Tallying everything up, this gives us a total bridge cost of about $233,087. Now that we have a design that works, let's look at improving and reducing our costs. Let's look at the bottom chord. The maximum force strength ratio is about 0.6. There's still a lot of room for reducing this. Not a lot of the members are fully utilized, and we can reduce the size of some of these members. Let's try making all the bottom chords carbon steel. Let's try to use a tube. Let's make these bottom chords a 190 by 9 tube size. Let's rerun our analysis. Again, this works. The cost is about $218,000. Let's go through a third iteration. Let's try to add a second grouping, a second product to the bottom chords. The end 2 members along the bottom chord at each side of a truss, there's still some reserve in these members. Let's try to reduce these down a little bit further. Let's try using a 140 by 140 by 7 carbon steel tube. Let's rerun our analysis. Again, our analysis works. The cost is a little bit lower still. It's about $213,900. Looking at the utilization ratio for the bottom chords, the bottom chords are just in tension. So when members only see tension force, it's usually best to use bars, rods, or plates for these members. And when you have members which are in compression, it's usually better to use a section such as tubes or a W section for these. The reason why is because members in tension, the tension force actually helps to stabilize the member. The resistance of a tension member is not dependent on its length. It's really just dependent on the grade of material which you use and the cross-sectional area of that member. So let's look at one of these members and the specific details for that member. Let's click on member details. This will show you the actual properties, the dimension, the cost, as well as the strength versus length of the member. So you can see what type of material you use in terms of the grade of steel, in terms of what size of section would you use, and what also as well the strength of this member versus its length. So this, in terms of this graph, you have 2 lines. You have a blue line along the very top. This is the resistance of the member in tension versus its length. As you can see, in terms of the strength versus the length of the member, it doesn't really change. It is a constant number. In terms of this second line, which is in red, this is the resistance of the member in compression. So you can see the shorter the member, the stronger it's going to be. The longer the member, the lower the resistance in compression. The reason why is that with members in compression, the longer the member, the greater the tendency for the member to buckle. Therefore, the longer the member is, the lower the capacity is going to be in compression. With members in compression, the resistance is based not only on the grade of steel and the area of that member, but also on how that area is distributed about the cross section of that member. The further the material is distributed away from the center of the section, the stiffer the member is going to be, and the less the tendency the member has to buckle. Considering that the cost per kg for bars is lower than that for tubes, it's usually more economical to use bars where you have members of your bridge just in tension alone. So what we're going to do is that we're going to change all the bottom chords. We're going to use bar sections. We're going to use an 80 by 80 size bar. For the end two members along the bottom chord, we're going to use a 70 by 70 bar. We're going to rerun our analysis. Again, our design works. Our total cost is about $210,000. So let's go through another iteration. Let's start changing the geometry now. Let's change the geometry of this truss a little bit. The way you can do that, you can actually move your joints around a little bit. If you left click on a joint, you can actually use the up, down, left, or right arrows on your keyboard to move that joint around a little bit. I'm going to change the joints of my bridge. I'm going to keep the middle joints in the mid span of my bridge at 7 meters. The end joint, I'm going to change that to a height of 3.75 meters. The next joint over, I'm going to change to a height of 5.25 meters. And the next joint over, I'm going to change that to a height of 6.5 meters. I'm going to rerun my analysis. Again, my bridge works. I get a slightly lower cost now. The cost now is about $568. Iteration number 6, we're going to try to improve this bridge again, just a tad more. We're going to play around with the top chord sizes a little bit now. We're going to change all the top chords again to a carbon tube. We're going to use now instead a 220 by 220 by 11 tube. Let's rerun our analysis. Again, the bridge works. Our cost has dropped just a tad again. The cost now is about $199,000. For iteration number 7, our next iteration, next try on for this bridge, we're going to play around with the verticals now. We're going to change the verticals typically to a 100 by 100 by 5 carbon tube. For 3 of these verticals, we're going to increase these just a tad more. We're going to make these 120 by 120 by 6 tubes. Let's rerun our analysis. Again, our bridge works. The cost now is about $196,000. For our last iteration, iteration number 8, we're going to start playing around with some of the diagonals. For these typical diagonals, in terms of a typical size, we're going to make these a 120 by 120 by 6'2". For 2 of these panels, towards the very end, we're going to make these 140 by 140 by 7 tubes. We're going to rerun our analysis again. We see that our bridge works. In terms of this design, the cost is about $191,000. So just to let you know, for the winter 2016 term, when we use these same initial parameters, the best design for phase 1 from all the groups, from all sections in Civil 1232, the lowest cost we had was about $173,000. If we stopped at this point in our design in this video, we would have been ranked about 15 out of about 40 groups in all the 3 sections. In terms of a mark, we would have gotten about 80% for phase 1. For phase 1, depending on how competitive you are, you could really spend a lot of time or very little time on phase 1. Really depends on how keen and how competitive you are with the rest of your class. Another tip I'm going to give you, to reduce your costs, you want to also look into using other types of steel grades in your design. So just don't look at using carbon steel. Look into using other steel grades such as the high strength low alloy steel and the quench and tempered steel as well. Also look into perhaps increasing the number of joints in your bridge, perhaps placing more joints as strategic places in your bridge design as well. Both these will help in terms of your overall bridge cost. Also, you want to look into playing around with the geometries of your bridge in terms of the height versus the span of your bridge. So, for example, if we set our bridge height to be 10 meters instead of 7 meters, what would be the lowest cost? So, instead of going through this complete exercise, which we just did, have this example right here, whereby that's already done for us. It's basically the same geometry in terms of the bridge. In terms of the only main difference is the height of this bridge. It's gone from 7 meters to 10 meters. And going through that same process, I've tried to optimize the cost of this bridge. The cost, spending about 15-20 minutes on this, I got it down to about $196,000. Okay, so for this design, in terms of the costs, you're going to see that your top and bottom chords are a little bit lighter, but the web members are a little bit heavier. As another example, if we went to the other extreme, we made our bridge a little bit lower in height. So let's say instead of using 7 meters in height, we went to 4 meters. So this is a third example which I had. Again, the geometry of this bridge is about the same as before in terms of the panels and the overall geometry. The only main difference is the height of the bridge. The height at the middle is 4 meters versus 7 meters. Again, I went through that process of optimizing this bridge and I got it down without doing much work to about $212,000. For this design, the top and bottom chords are a little bit heavier, but the web members are lighter. In terms of the height versus span, there's an ideal range of heights versus spans which will minimize your bridge costs. You don't want to make your bridge too high or too low in terms of height. Doing either one is going to increase your overall cost of your bridge. All right, I think I gave you enough tips and ideas that now you can confidently go ahead and create and play around with Bridge Designer on your own. With that, I'm going to sign off. I hope that you learned a lot of good tips from this video, and I hope that you have a lot of fun with this first phase of the bridge contest.